So it's a pleasure for me, a real pleasure for me to introduce Professor Hermann Schuss-Valdez. Hermann works in the University of Erlangen and Nuremberg in Germany. And Hermann has been several times in Cuernavaca. And in particular, this year he has a sabbatical period for 6 months here in Cuernavaca. And he arrived in Cuernavaca last February. He will be until middle of July. Okay. And Hermann is one of the very well-known experts in mathematical physics about mathematics of topological insulators. And Hermann is going to speak about that precisely today. So the title of his course is Topological Insulators from the Perspective of Non-Commutative Geometry and Index Theory. So let me welcome Hermann and thank him for accepting to teach this course.
So thank you very much, Carlos, for introducing me, and to all of you for coming. And I'll hope to be able to communicate a little bit to you what topological insulators is. And now what was stressed actually both in what Carlos and what Rafael said was that you have a good analysis background, but on the other hand side, the whole school is called mathematical physics, and there's the word physics in it, and I think I will take roughly the first session, or at least the first half of the first session, to tell you about the physics of these systems, and that will be a bit rough description of what is a topological insulator, but I hope that this gets you interested then later on also in the mathematics, okay? The mathematics, they are actually not so much analysis like epsilons and deltas estimates. It's more a structural analysis that we do on these systems, okay? So, okay, there's a number of collaborators there that you can read there. You can also access the slides in case you're interested in doing that. On my website, you'll find a link to basically the same slides because, oh, yeah, okay. In any case, I don't think that would have been of much help against the cold air inside here, yeah? It would have just inhibited the warm air to come in. Okay, so on my website, you're going to find these slides in a slightly modified form. So you don't have to take notes if you don't want to, and actually, yeah. So let's start with a short overview of what I would like to tell you. I already said I want to tell you what a topological insulator is, okay? And tell you some of the main experimental facts, basic theoretical approach on the level of theoretical physics to describe this system, to get a little bit of a handle of what we're actually trying to do. And then today I think I'll tell you a lot about a one-dimensional model, which is a toy model, which is very simple, on which many of the structural things can be explained well, I think. Okay, this is the SSH model over there, and then this thing here. And then probably tomorrow, in the next days, I'll tell you more how you go to higher dimensions and what are then the techniques that you apply in order to describe these systems. So basically the mathematics that we'll be talking about quite a lot is K-theory, a little bit of index theory and non-commutative geometry. And well, these concepts from pure math, so to say, can be beautifully applied in the framework of these topological insulator systems and give you really a number of interesting and physically important connections between physically measurable observables in these systems. Okay, and I want to give you a little bit of the flavor on that. I can't tell you everything, but that's a little bit the aim of the lectures to get you interested in that. Okay. Okay, so let's go on. Well, this is the same thing. So what is a topological insulator? So first of all, you should think of electrons. So the only thing that about electrons is going to be crucial here is that they are fermions. Okay, so I'm talking about fermions, and actually most of the things will first be described in an independent particle picture. So this means that we're basically doing a one-particle theory. Okay, and the dimension of physical space will be very important. Depending on dimension, you have different phenomena. Okay, so we have a d-dimensional system of independent fermions. And well, what is important in the field is that there's some kind of a disorder. So what you should think of in the system, it's supposed to describe a solid state physics system. In this solid state physics system, you have impurities, you have disorder, and you want to take that into account, and it's important for the physics to do that. Okay? And moreover, in several of the more modern systems, you have a combination of basic symmetries in the system. So these are fundamental symmetries which are not like crystalline symmetries. They are more like a particle-hole symmetry, for example, which naturally arises when you describe superconductors in Bogoliubov-de Gennes framework. So you have particle-hole symmetry. You have a time reversal symmetry, okay, which is something that you also know intuitively. And I'll tell you how to implement that in quantum mechanics afterwards. And you might have something which is called a chiral symmetry, which is sublattice symmetry in the system, which also is very often in these systems. So you have a combination of these symmetries. So moreover, these are the electron systems, d dimensions, okay, disordered with possibly with symmetries. Moreover, they are insulators. So what means insulators? So one of the things that I hope you do know from quantum mechanics class or solid state physics class is that in a solid you have for the electron something like a Fermi level. Okay, it tells you fill up all the electron states, the fermionic states, up to a certain energy level, and then there are no particles left. And that fixes you an energy inside of the spectrum of a one-particle operator. It's called the Fermi level. And an insulator is when in that Fermi level you don't have any, either you don't have any states, like in a semiconductor, you have a gap in the spectrum. There's no states there where the particles can move, okay, and then it becomes an insulator. Or that at this level, the Fermi level, you only have states which can carry current, okay, so which are localized. Yeah? So these two facts, the second is a bit more general, make out an insulator, okay. Now these materials are called topological insulators, so there is something on top of that. There's topology, and the topology that we're talking about is a very rough topology. It's not like set theoretic topology. It's more like differential topology of very robust quantities like winding numbers and Chern numbers of vector bundles generalized in a non-commutative framework. Okay? And I'll tell you what that is. But there is some kind of a very robust topology in these systems, which is relevant for physical effects. The main thing which makes these topological materials interesting is that they have delocalized edge modes. So if you take these d-dimensional systems and you put them in a half space, on the surface of these systems, you can have supplementary states. You sort of have waves, which electron waves or particle waves, yeah, which travel along the boundaries of these systems, and these supplementary new states, which are there for topological reasons, they're extremely robust. So you can use these states also for technological applications. Okay? And I'll give you a flavor of that in a second. It's like an overview. Okay, and the interesting mathematics is what people call the bulk edge correspondence. It tells you how the topological invariance which you do calculate in systems in the infinite space, which are these winding numbers and Chern numbers, which I'll tell you, how they lead to the surface states, okay? This is a mathematical principle behind it, which is very beautiful, I think, and is which I try to explain to you. Okay, there are other effects. So other effects linked to this non-trivial topology are in particular bound states, like zero modes and Majorana states, and a huge number of other effects. I can't describe that. I mean, there has been an explosion in the physics literature within the last 10 years, I would say, about these type of models and about applications that you, not only models, they are also real materials, so there's also experimental work going on these. There's an explosion of works on trying to understand what the effect of this topology is. And moreover, it becomes very, very relevant for other type of physical systems. So what people understood is that basically, even though they started out with fermionic systems and described these in the realm of quantum mechanics of electrons, they realized that what is really important is that you have some sort of a wave equation behind it. In wave equations, you also have in classical physics or for bosons, for example, so for, say, light, where you can either describe it quantum mechanically or even classically just by Maxwell equation, which you can formulate as a wave equation. And whenever you have topology in these systems, which can be produced, you can have the same kind of phenomenology here. So in particular now, great activity goes on what is called topological photonics. So for systems where you have photons, which more or less can be described also in this framework and leads to very interesting applications. Okay? Maybe I'll give you a little hint on that a little bit later, or you can ask me afterwards. Okay, so these are basic experimental facts and a basic description what the topological insulator is. So there's, in some sense, the mother of all effects, which is already quite old, and which is the quantum Hall effect, which is the first topological insulator. It wasn't called a topological insulator. This was an effect which was described like 45 years ago now already. Actually, here's, well, it's more 47 years. Okay, so the picture is not very good, but I'll give you a schematic representation of that here, of the graphics. This was the original graph, which I downloaded from the internet. You can't see it anymore. It was very basic experimental observation. But let me describe you what this quantum Hall effect is now. You might have heard about it, but I think it's good to come back on that first and tell you what the quantum Hall effect is. Okay? So, well, Hall effect is the following simple thing. You have a sample. You carry a current through. So you push a voltage outside and you let electrons flow through the sample. Okay? And then there's a perpendicular magnetic field to the sample. And one thing that you do remember is that, well, a charged particle, like the electron, moving in a magnetic field leads to the Lorentz force. And there's what you can describe that by a Dreibein. Yeah? So you have the velocity, then the magnetic field, and then there's a force going to that direction. And that leads to a drift of the particles. Okay? And if the particles are charged, it moves the particles to one side of the sample. And therefore, you can measure a Hall tension, a tension from here over there. Right? This is the Hall tension. And here's a plot, a schematic plot of, well, what was on the previous transparency of what people measured in 1980. You see, this curve here is the Hall resistance. So it's the quotient between the voltage, between the current and the voltage. Yeah? And it's denoted R. And you see that it has certain steps here. It jumps up, 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 and then like that. That's the curve. Okay, that's what you measure. And that was quite a huge surprise in those days. Because typically you would see more or less a straight line. Okay? What do you vary here, actually? Well, there are several things that you can vary in these systems. You can vary either the magnetic field relatively easily, or you can also vary the number of particles. So I didn't tell you that, but maybe I should now, is that this solid-state system here is still quite small. Okay, it's like the order of a micron, and it's two-dimensional, but it's nevertheless a solid-state system. So how do you get a two-dimensional system of electrons in the lab? Well, you take two type of different semiconductors, and at the interface of these two semiconductors, there's something like a potential well. Okay? If they have different chemical potential, you have like a potential well. So if you had very low temperatures, the particle go into the fundamental of this into the fundamental of this potential well. Okay, it's like a harmonic oscillator. You go down in the fundamental state, and well, this is only to the transverse direction. In the two other directions, if you really have two solids sticking one on top of each other, in the in the horizontal directions, you can move. Okay, so the particle is in this fundamental state, effectively restricted to this 2D surface, so you can really make a model, quantum mechanical model, describing these systems by a 2D Hamiltonian operator. Okay, and we'll do that in a second. Okay, and okay, so what can you change? you can change the chemical potential if on these two solids you put what people call a gate voltage, yeah, then you can change the number of particles which are in the 2D surface. So that's also something that you can change macroscopically, okay? So you change two macroscopic parameters, the magnetic field and the particle density, that's down here, okay? It's the flux density that you can change. And you see an experimental curve like this, where here you have what people call plateaus. They are extremely flat. So that means that the relative error with which you can identify, which is flat, it's 10 to the power minus 8. It's extremely flat, really, okay? Over a large range of parameters here. And then there's a change, okay? And, well, the second remarkable thing, apart from being very flat, is that the flat plateau values of the Hall resistance, they take values which on the left-hand side here are not plotted very nicely, but maybe on the next transparency they are. They take values which are given by a fundamental physical constant, E square divided by H, Planck constants. Okay? So electron charge square divided by H. So that's very remarkable. So why is that so remarkable? Because this is a macroscopic experiment. It's not like you're taking an atom and you measure the lines inside of the atomic lines, where, of course, you also measure lines and you measure very fundamental constants, so to say. But this is more like a Bohr quantization in an atom or in a molecule, where you measure the lines of a molecule. Here, this is a solid-state system. It's a huge system. Even though it's only a micron, there are millions of electrons involved, yeah? And nevertheless, you have an extremely robust measurement of fundamental constants, okay? And the reason behind that is what people learned and afterwards, is that there's some topology in this system, okay? The quantization in this quantum Hall effect, quantum being the fact that you have here these flat lines, is not due to quantization as in an atom. It's due to the topological effects that the electron system has intrinsically. Okay, I'll tell you what those are. Okay, so it's a really remarkable experiment, and there are a number of Nobel Prizes associated with which I'll tell you afterwards. Okay, so most of the things I already told you. I mean, here are these two semiconductors. Here are, well, classically, these Lorentz force. Well, what does it lead to? Well, Lorentz force basically leads to something that you did in a classical mechanics class, that particles move on a cyclotron orbit. Okay? So inside of the sample, they move on a cyclotron orbit. And, well, if classically now these cyclotron orbits, if you picture them, yeah, like that, they should turn all in the same direction, then on the border, on the boundary, they are reflected classically. And you see what happens if they reflect. Well, then they jump off, but they turn in the same direction. So basically, you move along the boundary of this sample here. Okay? And I downloaded this from the internet. I didn't pay a lot of attention. The last time I talked about this, somebody said, hey, there's something wrong. Indeed, in this picture, something is really very, very wrong. I can't even see it from there, but you might be able. The arrows go here in this direction, yeah? But you see on the other side, the people draw the arrows in the same direction. So it looks like the current here goes in the same direction. But you see, if they all move in the same orientation, the arrows over here on the other side, they should go backwards. Okay, so you have one current flowing that direction and one going that direction. So the upper side here is wrong. Okay, good. I'll do a quantum mechanical model, a quantum mechanical description of this and how this leads to topological effects later in the course. Okay. Okay, so here's the Nobel Prizes as promised. So Van Glitzing, only 5 years after having done this experiment, got the prize for it. And then there's a fractional quantum Hall effect, which I'm not going to talk about. This year, or last year, Nobel Prize was given to Thouless for 2 contributions. One was linked to the explanation of this effect, because he found out the topology which is behind it, and I'll show you that later in the talks. Last year also Duncan Haldane got the Nobel Prize, so he came a little bit later, but he had the following discovery. He discovered that there exists something like the anomalous quantum Hall effect. That is a quantum Hall effect in a system which has no exterior magnetic field. Something which seemed completely necessary in what I described to you before is that you have an exterior magnetic field, so you have these cyclotron orbits. But what people know now is that it is also sufficient to have a magnetic material in the sense that there's locally a change of the magnetic field. So you have local magnetic field, a periodic magnetic field, due to magnetic properties of the atoms in the solid, okay? And that can also lead to a quantum Hall effect called the anomalous quantum Hall effect, which might have potentially a lot of applications, okay? So he got the prize for something very related. Not only that, he also has a second contribution, which is mentioned in the Haldane spin chain. Okay, another Nobel Prize, was given for graphene. Actually, on graphene, they did not study the quantum Hall effect immediately, but nowadays people have also studied the quantum Hall effect and graphene, found interesting properties there. I'm not going to talk a lot about that, but it's somehow in the related field. What is very remarkable is what I just said, is that this anomalous quantum Hall effect by now can be produced in particular materials, tin telluride, it's here, these tin germanium telluride samples, particular metals, not metals, particular materials, almost at room temperature, okay? And that's extremely important. Why? Because what I told you before is that in these quantum Hall physics, you do have these currents flowing along the boundaries of these systems. And if you can do that, and these currents, they're extremely stable. This is what we're basically going to describe, okay? And if you can do that at room temperature, you have materials which carry these currents, which are robust for topological reasons and can't be destroyed even at room temperature. So these are like superconductors, but not superconductors in the conventional way. They are topologically carry these currents like superconductors and can possibly, and people are dreaming about that nowadays, be the materials which lead to superconductor at room temperature, okay? And are much more promising and much more simple in some sense than materials that people looked at before. Okay, so this was quantum Hall physics. So let's give you an overview of more modern topological insulators. So what really got the field started is a groundbreaking work by Kane and Mell in the year 2005, where they discovered that, purely theoretical discovery, okay, where they discovered that even if the system has time reversal symmetry, okay, so no magnetic fields, not from the outside and not inside of the materials, really time reversal symmetry, yeah, then you might have non-trivial topology in the systems. So before people said, well, if there's no magnetic fields and there's time reversal, then there's no topology at all. There's nothing to be seen. But that turned out to be wrong. There's what people call now Z2 topology. And I'll try to explain you a little bit about what it is later on maybe. So there is some kind of a topology which is linked to real K theory, people say nowadays, yeah? It is also responsible for physical effects. So there's what people first thought. Ken Mell said, well, possibly you have this in graphene metals. It turned out that graphene is not the right material. The model that they had written down, which they showed had non-trivial topology, was just not fit to describe graphene because the parameters were not in the adequate range. But later on, there are other groups which said you should try in other materials, for example, this mercurium telluride samples, where actually they could measure these effects. Okay, so there's also interesting boundary physics, boundary states in these type of systems. Okay, and there's actually still going quite a lot of discussion on whether these experiments really showed what people think they show, yeah, and the situation experimentally is not so clear, and that's also one of the reasons probably. So in particular, there's a group in Rice around DO, which showed that certain, things which one would expect from theory don't happen. Namely, if you turn on the magnetic field, these boundary physics remains very stable. okay? And that should not be true if you talk about topology which is linked to something which is intrinsically related to time reversal symmetry. So the experimental situation is not so clear, I would say, which is also probably one of the reasons why the Nobel Prize for these people here was not given yet, okay? So they chose to go with the old guys last year. Okay, so well, maybe just one slide on what Majorana modes are and why they are important. So what is this, first of all? It's the following thing. I mean, this was an old proposal, actually, 2000, from Reed and Green, where they said if you have a superconductor, in the now more modern language, one would say a topological superconductor, which is a two-dimensional P plus IP wave superconductor, and one can write down an easy model and show what the topology is in the model, actually. Then, in these systems, attached to certain defects in the system, you added topological defect in these systems. Attached to these defects, you have bound states. And these are zero modes. These are what people call Majorana states. They are very robust states, eigenvalues of a Hamiltonian, which are localized in physical space and sit there and which can be used in order to manipulate them. Yes?
What is the Hamiltonian?
So the Hamiltonian, maybe I'll write it out for you later because it would get me a bit off, but I'll tell you the Hamiltonian if I get to it in the lectures. If not, I'll tell you on the blackboard. It's easy.
Is it Dirac model?
No, it's a tight binding model. Okay, it's very easy. It's actually in 2 dimensions. You take a 2x2 matrix of shift operators in 2 dimensions, and you realize that it has a gap, and that you realize that it's non-vanishing Chern number, and then you have to do an argument to show that you have these zero modes very robustly there. Okay, but you can do that precisely. So why are these modes so interesting? Well, because what people are dreaming about is that you can do quantum computing with them. Okay, so if you have several of such states, you can dream of moving them around and doing certain things with them, which I basically don't understand in great detail either, but I see roughly how the picture goes, how you can work with these states. And that's why people say, well, with these, one could potentially build a quantum computer. So it turned out that this initial proposal of Majorana modes in 2-dimensional superconductors is not very practical from an experimental point of view. But there's another situation, namely in 1-dimensional systems, which are 1-dimensional chains, which also are topological, and which actually I will be able to describe to you soon. In these 1-dimensional systems, you have bound states at the edges. And these edge states at the edges, they can be used just as well. Okay? And are also zero modes, Majorana zero modes, with which you can actually work. And these states have been exhibited in experiments. So there are several groups. The first one was Charlie Markos' group in Copenhagen, but afterwards there were quite a few other groups which were able to find and measure these systems, these bound states. And well, the story goes a bit on. So I put down here for you, you can download on the slide afterwards, a link to a Microsoft web page where they say the headline is Microsoft steps away from the chalkboard to create a quantum computer. Well, okay, you go and read the text. You find out roughly what they are doing. What they did is they hired, of the 3 groups which measured these edge modes on these superconducting chains, they hired 3 people. One of them is Charlie Markos. Brought them to Seattle and put them together in the lab. And now they are there doing experiments, trying to produce several of such modes and try to get them to interact. Okay, so that's basically what probably they are doing. Well, we don't know. Okay, so if you read a little bit, it says the text says the magic recipe involves a combination of semiconductors and superconductors. Okay, so they're not going to tell us what they are doing, but roughly people know that they try to build a quantum computer using the edge states of several of such quantum wires, and to have these interact between each other so that you can build a quantum computer within the state space of several of these zero modes. Okay, so that's more or less what these zero modes might be useful for. Okay, so then there's higher dimensional topological insulators. This is already a bit old, so 2013 or so, yeah. But you see there's lots of materials which people were able to produce which are candidates to have topological effects, which can potentially be used, okay? Whether it's all going to be realized, another question, but I mean, there's a lot of activity going on in the last years, much, much more even. Okay, so what I propose to do the next 10, 15 minutes is to talk about the basic theory of the quantum Hall effect, okay? This is a bit old-fashioned already, what I tell you. Yeah, I mean, maybe in basic solid-state physics class, you are being taught that nowadays. But I think it's an honest way to approach the problem for these guys, for you guys who might never have seen anything. So what I hope is that you have seen the Landau operator. Okay, here it is once again. Oops. This is the Landau operator. So this describes a particle in 2 dimensions, which is submitted to a magnetic field. So the magnetic field means you have to add a vector potential, which, well, you choose a gauge which describes your constant magnetic field. And one of the gauges that one can choose is the so-called Landau gauge here, where the vector potential, the 2 components are either one is 0 and the second one is just the position operator in the direction 1. Okay, so 1 direction, 2 direction, everything happens like on the plane. You have direction derivative 1 and directional derivative 2. So it's like the Laplacian if there would be no A in 2 dimensions, but then you add the vector potential. Okay, this is the Landau operator, and what is very important, I hope I'll explain you, is this disordered potential. What is a disordered potential? You just think of a potential which has some bumps and which is somehow random. Okay? Yeah. Okay, yeah, that is 1, isn't it? I could have put the mass equal to 1 as well. You're right. Yeah. And also, you see, there should be maybe an E here. Because in the gauge you have to put, I mean, either you have to put the, no, there's the E. Okay, sorry, I did put the E. Okay. But let's not worry about the constants too much, okay? So one of the things that one first can do with this operator, in particular if this disordered potential is not there, one can do a Fourier transform still, at least in one direction. I mean, the magnetic field, so this x1 here breaks the translation invariant in the 1 direction, but not in the 2 direction. In the 2 direction is still translation invariant because there's just the second derivative here, okay? So one can do a partial Fourier transform in direction 2, which I denote by F2, and what it does, it gives you a fibered operator, okay? This is like Bloch theory or Fourier theory. It gives you a direct integral over the Fourier parameter, which is K2, of one-dimensional operators which act in the 1 direction, yeah, which depend on K2. How does it depend on K2? Well, you just replace x2 by K2. Okay? That's what you're used to doing. And these fibered operator, okay, they are self-adjoint, one-dimensional, shifted harmonic oscillators simply because this thing is not there in the Landau gauge, yeah? So there's just here a potential where the K2 is the parameter which you change, and the x is there as a square, because here's a square. So it's a harmonic oscillator, but the origin is shifted. So the particle, the 1D particle, is in a harmonic potential well, which is located at K2, sorry. Okay, so here is the direction x1, and here is the potential. The potential, well, V of x1 of h of K2, which is the second derivative in the x1 direction up to a constant. And then this potential here, which depends on K2. Okay? Of course, I mean, you can do the analysis of this thing. It has harmonic oscillator levels. But now what happens is that if you change the K2, well, you shift the harmonic oscillator to the right or to the left. it doesn't change the energy levels. And therefore, the energy level is infinitely degenerate. Okay? You have an infinitely degenerate peak, and the spectrum of the Landau operator without disordered potential basically looks like this. You have the one dimension, here's the energy axis, yeah? Here's 0. You basically have the harmonic oscillator levels, 1/2, 3/2, 5/2, and so on, which are all infinitely degenerate. Okay? Due to the fact that this is, just shifted the harmonic potential. These are called the Landau levels. Okay? Landau levels. If you haven't done this analysis, you should do it once in detail to be sure that you understand. That's basic for this, the theory of the quantum Hall effect. Okay? Now, if you have these infinitely degenerate Landau levels here, well, you can take a spectral projection. Say you take a Reeds integral around it, you get here a spectral projection P, right? Which projects on all state inside of one Landau level. Let's choose the lowest one. This spectral projection turns out to be an integral operator with an integral kernel. You can calculate it explicitly. It's basically given by the eigenfunctions of the one-dimensional harmonic oscillator. So it's Hermite functions shifted around. Okay? And the thing which is very crucial now is that you can calculate something topological from this projection, this Landau projection. Namely, you calculate what is called a Chern number. So here's a formula. You take the projection, you commute it with the position operator x1 and the position operator x2. Okay? You have to check that these are actually bounded operators. It's true, because the integral kernel of P decays. Okay? You take the commutator of these integral kernels, you multiply once again by P, and you take the matrix element. So you take this as an integral operator, you take the matrix element 0, 0, the diagonal one. Okay? Not the matrix element, it's the integral kernel is continuous, and you take the point 0, 0 of it. Okay? Or if you write out explicitly down there with, well, here is x and y, it should also be x1 and x2 maybe, as the variables, the integral kernel is given by this, and this is a formula for what you calculate here actually. Okay? The point is that formula, you can calculate it explicitly, and it shows you that this integral, this strange integral here, or this formula, is equal to -1. Okay? Good. Well, there are many ways to calculate -1, but the important point is that a physicist looks at this kind of a formula, and he does realize that what is written there is actually the Hall conductance. Namely, if you take your two-dimensional electron system and you perturb it by an electric field, and it's inside of a magnetic field, which is perpendicular, you calculate in linear response theory the answer of the system. So you calculate the Hall conductance. You make from the microscopic theory, yeah, given by this Landau operator here, you calculate the macroscopic measurable quantity, and you realize it's given by a formula, and this turns out to be the formula. And therefore, these numbers, they're important, and actually, well, the fact that this is equal to an integer number is precisely the reason why in the experiment you have these flat plateaus. So you calculate that for one, I just calculate that for one projection, okay? Just for one projection here, you see, in the Landau operator. The very crucial point, which hopefully I'll give you a glance at later on, is that if now you add a disordered potential, you change the model dramatically. You can't do all this analysis, okay? Can't do that. But you can still write this formula here. And it turns out that this formula here is still an integer. It remains extremely robust. It's still an integer number, even though I change something dramatic in my system. I add this disordered potential, which is not a local perturbation like in scattering theory. It's something which can be everywhere in your system. Nevertheless, this type of a quantity down here doesn't change. And therefore, the Hall conductance is extremely robust under perturbations in the system. Okay? There's a mathematics behind that. Right, so what happens with the eigenvalues? Here you are. to be a little bit more concrete, I won't be extremely concrete. Huh? P.
The projection.
Ah, okay. I will show you. So let's first add the perturbation. Basically, the message is don't look too great at the detail. Any kind of perturbation which is somehow reasonable is okay. Of course, you have to do mathematical work on that, but one way to say is that you just take a potential bump in 2 dimension. Okay, so we are in 2 dimension, and imagine you take some kind of a little bump in a square of size 1. Okay. And let me call that V. Okay. This is the little bump function. Of course, in the energy value goes upside, perpendicular to the blackboard. Yeah. And then you shift it around. You move it in any side of the lattice. So you shift this bump from here to the next square. But you don't only just shift it. You also multiply with a number. This is a random number, omega n, which can be either large or it can be, say, down here, it could be negative. Okay? And then you do this in a random way. So this produces like a random potential landscape, which is supposed to model what happens really in these quantum Hall systems. Because, well, why? Why is it actually so? Well, because the 2D system, as I told you, was built from 2 semiconductors which are put on top of each other, which are really dirty semiconductors. They're doped. They're made disordered on purpose. Okay? Doping means that you add other atoms inside of the system and you put them at random spots, roughly. Okay? So it's kind of reasonable to take some kind of a model like this. So that's the model. Now, what's the effect of the spectrum? Well, if these omegas get larger and larger, it's going to spread the spectrum. Okay? So the spectrum is going to spread here on every kind of an interval. And the most interesting regime, which is actually also what is happening in the experimental situation, is that the spectrum becomes just a line. Okay? So you fill the gaps completely. Okay? So after a sufficiently large perturbation, the spectrum looks, as a set, looks completely boring. It's a half line. Okay. However, what is maybe more interesting to look at is the density of states. So without this order, the density of states consisted of these Landau levels, which are just Dirac peaks, 1, 2, 3, and so on. Okay. So you have these Dirac peaks there without disorder. As you add the disorder, spectrum is going to appear to the left and right, and at the end, well, it might fill all the gaps and give you quite a few states here. Okay? So you have lots of states. Density of states looks like that. And now, how do you choose the Fermi projection? Well, you choose the Fermi projection here. Somewhere there. Well, that's measurable functional calculus. Yeah? You don't have a gap there. But the Fermi projection might nevertheless be such that this formula for the Hall conductance actually makes sense. Well, it's not trivial for it to make sense. Why? Because you have here commutators with x1 and x2 which grow very fast to the outside, so there better be some kind of a decay for the projection for this thing to make sense. Okay? And what makes sense, well, if you have a gap, is that you have so-called Combs-Thomas estimates which tell you that the Fermi projection does decay, yeah, off the diagonal. But if you don't have that in this regime, there's what people call Anderson localization, which means that inside here you have lots of localized states. The spectrum is not absolute continuous with wave functions which are spread out everywhere, but the spectrum consists of eigenvalues which lie inside of the real line, like the rationals lie inside of the real numbers. And at each of these eigenvalues, you do have an eigenvalue, which is nicely localized. And because it's so, you can check that the Fermi projection actually has sufficient decay such that the Chern number is still defined. Okay? And then mathematically, to conclude that, you can prove the following thing. If you're inside of a regime of Anderson localization, as you move through the Fermi level here, you move it through here in an interval, which means you change the number of particles, this Chern number remains the same. It's constant. Why? Because basically all you do is you add localized particles to your system which cannot participate in transport in the system. Okay, that's intuitively the explanation. If you add particles, but they just are forced to sit at certain space regions, they can't change the Hall conductance, which is a global, a global measurement on the conductive properties of the system. Okay, so now.
So you have dense pure point spectrum in this?
Yes, but I should say that nobody is able to prove that you have dense point spectrum. Okay, what people are able to prove in the business of Anderson localization is very disappointing. All they know how to do is what happens all the way down here at the bottom of the spectrum. So they have Lifshitz tails, which is something which they allow them to start a multi-scale analysis and prove localization. But okay, we all know, so let's say the mathematical physics community knows that proving localization in 2 dimensions is one of the hardest issues there is, okay? Nobody is able to do that. And it's the same problem here in 2 dimensions with the magnetic field, basically, okay? But we can use it as an input. We know what localization is. We can characterize it. It means that the mean square displacement is bounded. If you have mean square displacement which is bounded, in a given spectral region, then what I told you is true. Namely, you can change the Fermi level through that region, and the Chern number will not change. Okay? So this was already a bit of math on the side of this physics explanations. But so what you should understand is the following thing, that it's very important here to have localized states. Why? Because in your experiment, you change from the outside the number of particles that you add in the system. You add them, but all the states that you add, they are localized states. Because they're localized states, they don't contribute to the conductive properties. And therefore, the conductive properties, they are constant. And actually, both conductances are constant. If we go back to this picture, one is the Hall conductance, which is constant, which is plotted down here is the direct conductance. The direct conductance is also constant, and it's actually vanishing there. Okay? Because you have at these energies, at low temperature, only particles at the Fermi level which participate, and they're all localized. So there's no conductance there. So that fits perfectly together. Okay? So I think not only on the theoretical side, people believe that they completely understand that. I think we also have very nice mathematical theory for that nowadays. So let's see what else. So I told you something about edges. So I want to do a very rough description of edge physics now, okay? By working with the same kind of a model. Namely, we had this Landau operator. And now all we do in this Landau operator is we cut it in half, so to say. It was an operator on the 2-dimensional system. Now we cut it in half. And we do it in such a way that we still have the translation invariant in the 2 direction. Okay? Therefore, we choose the Landau gauge. X1 was in there, but not the X2. So if I restrict in the one direction, if I restrict in the, how should I do that? Wait a second. Apparently, if I restrict in the 2 direction, I can still do the Fourier transform. So this, no, sorry, in the 1 direction. Sorry, in the 1 direction I restrict here, okay? So what does that mean? We have this, we do this Fourier transform just as before. It means that we basically obtain the same operators h of k2. They have a hat here because they are on a half space now. So this means that this part here is simply not an allowed region, okay? We cut the system in half. Technically, you can put some boundary conditions, say Dirichlet boundary conditions. You could also add a confining potential. It's basically not important what you do there, okay, for what follows. But let's say we add a Dirichlet boundary condition. And then what is this operator? Well, what is this operator? It's still a harmonic oscillator, but cut, as I said. And you see, something must happen with the spectrum now. It's the operator with this potential. So let me put a hat on top here now. Okay. It still has a fundamental sitting down here, but because it is cut off here, it will be energetically shifted a little bit up, no matter where I am. But if I move it all the way to the right, well, the boundary is very far away. So the effect of the boundary on the fundamental will be extremely small. On the other hand side, if I move it to the left, well, at the end, I'll have something like this. The fundamental will sit right here next to the boundary. Okay? And if it sits right here next to the boundary, it's going to be energetically moved up. So here's the spectrum, what you get. Here's, as a function of the K2 parameter, yeah, this one here, K2, the energy bands. So it converges to large K2s to the energy levels of the Landau operators. So there are these lines here. It's 1/2, 3/2, 5/2, and so on. To infinity, you have they converge to that, okay? Which corresponds to this picture also here. You just move it away. The fundamental will sit all the way down here, and the effect at the boundary is extremely small. Okay? But then if you move up, if you move to the left, the fundamental, for example, goes up, and it bends like this. Yeah? You move it over here, the fundamental moves up and up and up energetically. Okay, well, that's basic spectral analysis that you can do for these half-space operators. You can actually write out also what the eigenfunctions is. There's some special functions, Whittaker functions, which are associated to that. You can analyze these energy curves. Well, what for us is important is that you see these states here, they have a slope. It's here negative. And what is this slope for? Well, if you calculate the phase velocity of these states, which are, say, here, yeah, it's given by the derivative with respect to the quasi-momentum, K2. So these energies have the same slope. This really means that the particles, they travel in one direction along the boundary. Okay? They're all boundary states by this picture. You can actually also prove that. But moreover, they have a velocity going in the same direction. So they travel along the boundaries, which was the picture that we had before on the two boundaries of our systems. Okay? Of course, we need a model for one boundary now, but that's mathematically the most reasonable thing to do. Because the other thing is far away, and by tunnel effect, you have very little interaction between the left and right boundary in these systems. So it's better to do a model on just half space. Yeah, okay. And well, if you calculate then the current in the way that I'll describe later on, then you realize that here actually in these states you have a quantum of current flowing along the boundary. So you have one channel of conduction which is very robust along the boundary of this system. Okay? And associated to that you can do beautiful, simple mathematical theory actually. So I wanted to tell you a little bit also about discrete models, because what I'm doing afterwards is I'm doing what many solid-state physicists do, is they say, I don't want to work with differential operators. It's too complicated for me, and it's irrelevant. Why? Because we're just interested in low-energy physics anyway. So it's much easier to work in a tight binding representation, which are models which as models for a mathematician are not defined on a large L2 over RD, but they're defined on a lattice Hilbert space, so a little L2 of ZD. And there's actually a theory behind it, how to get that, yeah, how to get these effective tight binding models. But what I will do is I will just work with tight binding models on a simpler Hilbert space, which is the lattice Hilbert space. And I want to give you a little bit the description of the easiest model there is for the quantum Hall effect, which falls into this class. And that's the so-called Harper model. Here it is. So you're in, as I said, in 2 dimensions. We just suppose that we have a lattice. So the lattice, on each side of the lattice in this model here, we just have one single state, yeah? One state. And, well, you want to have some kind of a kinetic operator. So usually we had the Laplacian in 2 dimensions. Now we want a discrete approximation. All that you do is you use so-called hopping terms, which allow the particle to move around to the left, to the right, and to the down, up and down. Okay, these are these operators U1, which is shift up on the lattice, and U1 star is shift down on the lattice. So to write the formula, U1 acting on a state localized at site N1, N2, okay, which is 1 point in Z2, just moves the state one side up. Okay, so this would be the shift. Yeah? And you have it in the 1 and the 2 direction. Now there's something else here. We want a magnetic field. So this shift is not completely sufficient, but what you want is actually, if you go around one of these squares like that, you want that inside, the magnetic field that is inside here, you want to feel it. And that is taken care of by adding a phase, namely which is the integral of the phase around it. You know that if you have, for differential operators, you can calculate the phase by going around a given region. You calculate the phase inside, basically. Yeah? Here you do the same thing. So this U is actually modified. You add here a phase factor. Okay, something which you have to add up here. And this is what is done here. So the shift operators are really the shift operators that I had here. And actually U1, I want the Landau gauge would be to choose in the 1 direction no phase factor at all. But in the 2 direction, we use a phase factor which is given by, like in the slide before for the continuous operator, which depends on x1, the position operator on the lattice in the x direction. Yeah? You know what it is? I mean, I don't know what the x1 on n1, n2 is, the operator which spits you out the same state, but multiplies it by n1. It's the 1 direction, so the 1 component is multiplied out. And you do this, you multiply it by basically the magnetic field, which is just the phase through the sample. So these 2 operators, the shifts, yeah, if you write out what that means, this phase, it means that U1 and U2, they do not commute like for the shifts, but they only commute up to a phase. And the phase, if you do the calculation, turns out to be this magnetic field which is in here. Okay? So that's the only thing that you change to a discrete Laplacian, one would say here. With the magnetic fields, you change these commutation relation to that one. And then, well, if you have chosen it like this, you can still do a Bloch-Fourier transform now on the lattice, on this operator, to do spectral analysis. And if the B is rational, you can still, if it's a rational number, times 2 pi, you can still do a Bloch-Fourier analysis also in the other direction. Okay? And then you find a band spectrum. Here's a famous picture, which is the spectrum of this operator here, plotted in, here's the energy axis. This thing here is the energy axis. And here is the magnetic field. Now, of course, if you change the magnetic field, that means that you change the commutation relations. And for rational values, I can calculate the spectrum numerically on a computer. And it gives you this nice picture, okay? Actually, this is only for rational values. You plot here the spectrum, and you see it's a certain collection of intervals. I think we'll have a series of lectures on this picture here in Lana Zhitominskaya's talk. But basically what she will tell you is that she doesn't know how to describe this picture. Because what people in analysis know how to do is to describe other cases of the so-called Harper model, but not this critical one here. Okay? Well, of course, many things are known also about this, but there are also many interesting things which are not known. Okay, now what happens afterwards with this model? Well, here you see you have lots of gaps. Because you have lots of gaps, you can use the Fermi projection onto these gaps, so on the spectrum below a given energy. And you can use this Fermi projection to calculate the Chern numbers by the same formula that we did before. Okay? It's this formula, the Chern number of P was 2 pi I times the matrix element of P, commutator of x1P and x2P. Okay? And here now the zeros is really the zero on the lattice. You just take that matrix element of the thing. Okay? And it gives you Chern numbers. Look, that's what you get. You take this Chern number. I didn't have to write it. It's always an integer number. To each integer number, you associate a color. And these people here, Yossi Avron and Osadchi, they chose, well, for 1, they choose color blue. For -1, they chose color red. And then there are other colors in here. Unfortunately, the picture is not quite nice here, not strong enough, the beamer. But I mean, gives you a beautiful picture which shows you in which region of this Hofstadter butterfly, which was the spectrum that I had on the last slide, you have a given Chern number. Okay? Good. So the other thing that you can do, so you can calculate these numbers, and there's a nice theory how to calculate these numbers also. Okay. What you can also do is afterwards restrict this operator to a half space again. What will happen if you restrict it to a half space like we did before is that all the gaps will actually fill. Okay? They will fill with spectrum, sorry. They fill with spectrum, so here's a picture like this. Here's one band, and here's the second band. Say you have a rational magnetic field, you have 2 such bands. Inside of a gap, you will have certain number of edge states filling up the gaps. So on a spectral level, the operator on a half space is not very interesting because the spectrum is just an interval. However, certain parts of the spectrum where the gaps were before are filled with very thin spectrum, which in density of states doesn't appear, and which are these bands of edge states. And the basic fact is the connection which I didn't say before, which I should have said, I'll comment on now, is that you can predict how many of these edge states there are. Namely, if you count their number and weigh it by the orientation, whether it goes down or up, this weighted number of edge channel bands is exactly equal to the Chern number. So something which you calculate from the bulk of the model. Okay? So let's look at this connection over on the Landau operator. Well, we had these Landau bands. If you go, say, in one gap, say we go into of this gap here, you have 3 Landau bands below there. You check that each Landau band has a Chern number equal to 1 or -1. Okay? And indeed, there are, in this gap above that Chern number, there are 3 bands, 1, 2, 3. So there are 3 bands of edge states oriented in the same direction, corresponding to a Chern number equal to 3 at that energy. Over here is the same thing, but it's much more complicated actually to realize that it's true. If you go inside one of the gaps of the Hofstadter butterfly, so you go here, and you put this Hofstadter butterfly in a half space, you have here Chern number equal to 1, you know that there's one band of edge states which is going to lie inside of this gap everywhere here, which is going to give you a Chern, which is going to give you one edge channel oriented in one direction. Okay? So that's a deep fact. That's a deep fact actually linked to this bulk boundary correspondence in 2-dimensional systems. Okay, so I also told you something. So this was the quantum Hall effect and the description of the quantum Hall effect by tight binding models now. Now I told you also about this anomalous quantum Hall effect, and to have something concrete, let me basically tell you what was half the Nobel Prize. It's a paper of 5 pages by Haldane, yeah, where he wrote down basically this operator here. Okay, so you see there's the shift operators, shift 1 and shift 2, on the lattice. Yeah, it's on L2 of Z2. However, it's a matrix. It has 2 degrees of freedom over every lattice side. So you have over here on each side of the lattice, you have 2 atomic levels. And well, the operator has shift operators in here, which don't lead to a global magnetic field. And over here, you do have magnetic phases, but they are local, so to say. They produce you a periodic model, a periodic magnetic field on the lattice. Okay? So they are basically, well, what type of parameters you can, I chose the parameters of the picture that I downloaded somewhere. There's M and T2, which are these coefficients. You can take the quotient by taking out the constant. So it's M divided by T2 is one parameter. And the other parameter is this phase. So there's e to the power I phi there. And this phase factor is also something that you can modify in your model, in this simple model. Okay. There's also an S3 here. There's a sum, you see an S3, that's the next nearest neighbor hopping, which is given by S1, S2. Okay, so you go two sides, first left and then up. Okay. And well, what is important is that this model here has a central gap. The energy 0 is not in this spectrum, except for certain particular values of phi. And you can therefore calculate a Chern number by the same formula. And this is the picture that you get. As you change phi and the M over T2, there are certain phase transitions. If this parameter is large, you have Chern number which is 0, up here and down here. But then there are other regions where the Chern number is 1 and minus 1. Okay? And if this Chern number is 1 or minus 1, you can use the same theory that I described before to reproduce surface states in this simple model if you restrict it to a half space. Okay? And therefore, if this model here describes a real material, this material will have surface states. And more of these surface states will be extremely robust. Okay? So this is the anomalous quantum Hall effect. So what are these more fancy new models? I told you about Kane and Mel. Well, one way to describe this is to take this model that I had before of Haldane, and you double it. You take once this model, and once you take the complex conjugate. And then you add a term which breaks the diagonal character, but which doesn't break time reversal symmetry. Basically, you take the Haldane model twice, one for spin down and one for spin up. And then you add an interaction term which mixes the two spins, but which does respect time reversal symmetry. Okay? So this is the Kane-Mel model. It has a time reversal symmetry built in. I didn't write out that in detail, but that's what can be done with this so-called rush bar spin-orbit coupling. And, well, it still has a gap, just like the Haldane model. Also, if this term is small, this gap isn't going to disappear. I just have two copies of the same thing, basically. And inside of the middle, you have two states. Well, if you're in the non-trivial phase of the Haldane model, at least. One is going up, and because in the second, I mean, one is an edge band going up, and because here you have a complex conjugate, which means reversing the local magnetic fields. You change the phi to minus phi, so you change the orientation also of the edge states associated. So the second band of states goes down. So you have a cross of bands. So typically what would happen if you have such a cross, if you think of basic perturbation theory, such a cross would dissolve. Okay? And then you would also all of a sudden produce a gap. And if there's a gap opened, say by adding this Rushbar term here, if there's a gap which opens, then there are no states at the Fermi level anymore, at energy 0. Okay? So no more interesting boundary physics. The point is that if this perturbation is chosen such that the time reversal is not broken, this cross cannot be dissolved. Okay? That's what one can do actually by very simple also quantum mechanical models. You can cook up a model in order to understand what I say. That time reversal symmetry will not break this type of a cross here. And because it doesn't, and because this cross again is extremely robust also against perturbation by disorder, yeah, you have these surface states at your disposal in these type of models and in the materials which are described by them. Okay? Good. So maybe I'll skip this because I have like 15 minutes about, and let's be a bit concrete about this one-dimensional model and show you roughly what the mathematical structures are behind this correspondence between the bulk topology and the edge modes on a simple example. Okay? So the simple example is now this Su-Schrieffer-Heeger model, which was developed to describe conducting polymers. And, well, it acts on a Hilbert space L2 of Z, but also has a two-dimensional fiber. So because I'm in one dimension, I just have one shift operator on the lattice, shift to the right, and then there's shift to the left, which is the adjoint. But it acts in a non-trivial way on the matrix degree of freedom, so the two sides that I have per lattice, yeah. And, well, they're the Pauli matrices, sigma 1 and I sigma 2 there. And then there's a mass term, okay? If you write it in the grading of the Pauli matrices, the Hamiltonian just looks like this, very simple. You have the shift to the right in the upper right corner, shifted by the mass term, and you have the shift to the left on the other side, shifted by the mass term. So that's already the model. Very simple. What is crucial is that this model is off-diagonal. And this off-diagonal means that it has a symmetry. There's a symmetry. The symmetry is a so-called chiral symmetry. Namely, if you take the Pauli matrix sigma 3, which is 1, 0, 0, minus 1, yeah? If you conjugate the Hamiltonian with that, you see it produces you minus the Hamiltonian. Okay? That's it. Easy to check. And actually, whenever this symmetry is satisfied, it just means that the Hamiltonian, this 2 by 2 matrix, is off-diagonal. Okay? Why is that so important? Well, because if my Hamiltonian is invertible, so I have an insulator at zero energy, there are no states. So I have an insulator, I have a gap there. That means that these off-diagonal entries here, they are also invertible. Well, if it's invertible in an invertible operator, you can find some topology in general. Okay? I'll tell you how. But here's a very easy way to see the topology in this translation invariant model. So here, translation invariant means that the mass is constant. Okay? It doesn't depend on the site. There's no random potential or anything which breaks translation invariant. So I can do a Fourier transform as we did before. Well, Fourier transform does what? It just replaces the shift here by e to the power ik. Okay? And the mass term is constant, so it just stays there. You have a direct integral over the Brillouin zone, which is just interval from minus pi to pi here, of 2 by 2 matrices, well, which are given by these matrices. Now, how can you get any topology out of that? Well, just look at the winding number of this thing here. You see this function here as a function of k is in the complex plane something which winds around once around the origin. Yeah? So the image of this thing here is in the complex plane, the point IM somewhere, which is here. And then you have a circle of radius 1 around it, and it can have a winding number. Of course, if you change the mass, you make it large, there's no winding around 0. If you make it very negative, there's no winding. So there's some kind of a phase transition. Actually, at these points, the gap of the model closes. Okay? But the topology is simply this winding number. Okay? It can be either minus 1 or 0. Or, given by the formula, as I said here. How's that connected to bound states? Well, here's a very elementary thing. I take my Hamiltonian, the same as before, and I restrict it to a half space. Restriction to a half space just means that I changed z here into n. Okay? So we took Dirichlet boundary condition. We just chopped it off. So the S is the unilateral shift. Okay? That's the only thing which changed now. And, well, obviously, the model still is chiral. It still has this, it's off-diagonal. That hasn't changed. So I still have the chiral symmetry. So let's first look at this situation where m is equal to 0. Well, if m is equal to 0, there's just shift hat and shift hat star. Why is it interesting to look at that? Because you see the left shift, which is S star, has a kernel. So you see, if you shift to the left, you subtract minus 1 here. Yeah? And if on the left-hand side there's nothing, if you go from side 0 to side minus 1, you can't jump there, so there's a kernel. So the shift hat is what people call a partial isometry. It's not an isometry anymore, not a unitary as before. It's a partial isometry. It has a kernel. Why is that kernel interesting? Because if this thing here has a kernel, well, I have a state which is given, well, here it's written, it's the initial state on the origin, yeah, the state on the origin, and here is a 0. So the first 0 is really the state at the origin, the second one is just a 0 entry, okay? That's in the kernel of the operator up here with m equal to 0. Right? It's trivial to check that, to see that, because it's in the kernel of this thing. Nothing happens with that part. So what does that mean? Well, that means that this Hamiltonian there has a surface state, which here really is localized exactly at the boundary. And of course, we only calculated that now for a very, very particular situation. So here's the spectrum, first of H. So here's 0. The chiral symmetry, as it reflects H in its negative, means that the spectrum is always symmetric like that. And now, if you go to the spectrum of the operator with a half space, you add one state here. The other thing is the same, okay? This remains the same. So there's one state added there. In a very particular situation for m equal to 0, but let's change m. Let's change m. Well, if you change m, of course, this state here will move. It will move. However, there's a problem. Why? Because if I start moving it to the right-hand side here, because the operator still has the chiral symmetry, this chiral symmetry in particular implies that the spectrum of H hat is always equal to its negative. So if this state here moves out, it has to have a friend over on the other side. There would have to be a partner. But I can't produce by small perturbation out of one state 2 states. Okay? So conclusion in this naive picture, but it's perfectly okay, yeah, is this state cannot move. It's pinned to 0 energy. It stays there. It is a 0 mode, which is extremely stable. Okay? Robust. So, and how many states do we have? Well, you check a little bit more in detail. You have exactly one state. And you realize that in a more general class of models, actually the following is true. The winding number that I calculated from the Borg model, where there was no boundary condition, is some topology that is in there in the chiral model without boundary condition, yeah, is equal to the number of boundary states. So how should I calculate the number of boundary states? Well, actually, I should calculate the number of boundary states, but weigh them with their chirality. Because the boundary states that we have here, it is in the eigenspace of sigma 3 with eigenvalue 1, so it has a positive chirality. What you can do by a generic perturbation is that you produce here new states, one with positive and one with negative chirality, such that the total chirality here will not change. Okay? That's possible. It's non-generic, but it might happen. So the general fact, which I want to explain you, is this. The winding number in the bulk is given by the total chirality of the boundary states. Okay? So up to now, everything was easy. We could calculate things explicitly. Now let's make the model a bit more complicated and add random mass terms. Okay? Just some kind of randomness in the model. So instead of having the mass constant, we now have it random numbers. Okay? The randomness introduced in such a way that the model still is chiral. Okay? So this chiral symmetry for the random model with random masses is still true. So the operator is still off-diagonal, but the off-diagonal entries, they are not as easy to analyze now anymore. However, one thing that is still true is that they are still invertible. Okay? If the mass is small, the energy bands, they might, after perturbation, by random perturbations, they might move out a bit. So the spectrum becomes maybe a little bit larger. So this would be the spectrum of the random operator. Yeah? But the gap here doesn't close yet, necessarily. And now, that means that A is invertible, because if H is invertible, if there's no spectrum, then the A is invertible. And now I can calculate,
A is just S plus I.
yes, S plus the random mass terms, basically. Right, exactly. It's just to have some generic invertible operator there.
Because you did not introduce.
Right. Yeah. But you take this, you write it out. It's exactly that. And it's invertible. So what I claim is you can calculate a winding number for that as well by this formula down here. So what did we do before? How do you calculate the winding of a function? Well, the winding of a function, which is invertible, is basically that you calculate the function of an interval into the complex plane, invertible, has a 1 form, which is this thing here, and you just integrate it, and this is the winding number up to constant factors, okay? So we can use that formula also for our models down here. Instead of the derivative, you take the commutator with the position operator in the one direction that we have. There's just one dimension here, okay? So it's x. You take the commutator, multiplied by I, multiplied by a minus 1, which is this thing here. Well, it's a 2 by 2 matrix. You trace it out, and then you take the expectation over the randomness to make it more stable. Actually, you can check that this is an almost sure number also. The point is that even though if you look at this formula and you would say, oh, there's lots of randomness in there and I don't know what I'm calculating, is that this thing is still an integer number. Okay? So there's, in the classical setting for this winding number, there's something called the Gochberg-Krein index theorem, or Noether-Gochberg-Krein, I should say. He was the first to prove it, yeah? And it tells you that the winding of a function f can be calculated as the index of a Fredholm operator, which is the function projected down to Hardy space. Okay? So pi is the projection on Hardy space, which are the positive frequencies. So it's on L2 of n, is projected on half space. You look at this projection to the left and the right. This thing is a Fredholm operator. Its index is equal to 1 and is equal to this Chern number that I wrote down there. And this index is, of course, random, but you can check that almost surely it's a constant. It's the same random number. Okay? And then you go on. So let me ask, how much do you guys know about the index of a Fredholm operator? Be honest, the students, I mean. Not that much. So maybe I won't talk about it now, but maybe tomorrow I spend 10 minutes. Is it better or to do that tomorrow? Yeah. So I'll tell you more about what this thing is, but this is a fundamental functional analytic concept that you should know or learn at least, okay? And you can prove these index theorems here. So once you have done that, so how do you go on now? This was something which tells you that I can calculate a topological quantity for my chiral Hamiltonian in one dimension. So now let's restrict this random operator to a half space. And indeed, you can prove the same thing as before, namely this non-commutative winding number, okay, which I also call the first Chern number, which is also this index, is equal to the chirality of the boundary states. So you go in the random model and, well, you look at the states which are exactly at 0. You count them, weighted by their chirality, gives you a number, which is here on the right-hand side, and it's equal to this Chern number. So the topology in these bulk bands here, given by this winding number, allows you to predict how many states you have here. In particular, if this is 1, there must be one state here. So it also provides you an existence criterion for having a state here. Okay? So the topology implies that I must have interesting physics sitting there. Okay? And, well, this is a very structural and robust result. And I'm coming close to the end of my time to talk now. But, okay, this is explanation of the index, which I'll do tomorrow. But just as a quick view of what we'll do then tomorrow morning is that behind this, there's actually a beautiful mathematical structure which is called the so-called triplets extension. And this triplets extension is an exact sequence of operators which connects you the bulk and the boundary of the system. And if you look into the K-theory of this exact sequence, it allows you to give a very structural explanation of the simple fact in one dimension that I could explain. The point is that this nice mathematical framework, even though in one dimension you could produce things in another way, does transpose also to higher dimension and allows you to produce many interesting results, I think, in higher dimension as well. Okay? So this is what I'll explain you tomorrow. But of course, I'll tell you first what the index is and then what K-theory is actually. Okay? Any questions right now? Or comments or wishes? Yes?
So do we need, in one dimension, do we need the spin, or can we have topological effect without spin?
No, if you would have to have, okay, so the 2 degrees of freedom, okay, you can view them as a spin, doesn't really have to be spin. Actually, in the classical model here, it's more like a bipartite structure of the system. So in this polymers, you have two atomic cells, which are different, okay, and they come one after the other. So it's more like a bipartite structure. So typically, this chiral symmetry doesn't come. I mean, these two degrees of freedom in the matrices, they don't come from spin. Okay, but you do need 2 degrees of freedom in one dimension in order to have a chiral symmetry. I mean, that's correct. Oh, good.